Hey everyone, welcome back, and today let's solve Leetcode problem 1861 titled Rotating the Box. So we're given an M by N matrix of characters box representing a side view of a box. And each cell of the box is one of the following. It's either going to be a string of a hashtag, which represents a stone at that cell. Either the cell is going to be a stationary obstacle, which is represented by a string asterisk, or it's going to be an empty cell, which is represented by a period. So the box is rotated 90 degrees clockwise, causing some of the stones to fall due to gravity. And each stone falls down until it lands on an obstacle, another stone, or the bottom of the box. And gravity does not affect the obstacle's positions, and the inertia from the box's rotation does not affect the stone's horizontal positions. So it is guaranteed that each stone in the box rests on an obstacle, another stone, or the bottom of the box. And we need to return an N by M matrix representing the box after the rotation is described above. So, honestly, this is pretty crazy of an explanation. I think it really is just best understood with an example. And so let's just go ahead and dive straight into the example here. So in example 1, they also give us an image to better visualize this in these examples. So we have an initial box input matrix to be basically 3 different actual cells, right? First, in the first cell, we have a stone, which is represented by this hashtag. In the second cell, we have an empty cell, which is represented by this dot or this period. And in the final cell, we have another stone or hashtag. And we're going to output this. Why do we output this matrix? Well, because we have to actually rotate it 90 degrees clockwise, which is why it says, although we're given an input matrix of dimensions m by n, our output is going to be having dimensions of n by n. N by n, not m by n. Why is that? Well, because we're flipping or rotating this input matrix 90 degrees clockwise for every test case. So instead of being 1 by 3, it would become 3 by 1. Or instead of being 3 by 1, it would become 1 by 3 as our output. So now let's actually talk about how we get these values inside our cells of our output. Well, we see here that in this example image that we have our initial stone right here, then we have an empty cell, then we have a stone right here at the bottom of our input matrix. Again, the bottom after we actually rotate it 90 degrees. Well, initially, once we actually start, our stone will be placed on the top of this matrix right here. Well, we know that the stone can't fall down because it's not being obstructed by another stone at this cell or an obstacle at this cell, because of course we don't have another stone at the cell, it's empty, and we don't have another obstacle. So we can bring or move this cell down to the bottom cell, the cell adjacent bottom to it, and keep doing that while it's not obstructed, while we don't have an obstacle or another stone at the next cell or the next index, right? And that's the reason why we can just drop this down 1, because there's nothing obstructing it, and simply return this. And this cell would go from containing a stone to being empty. Why? Because, well, we're shifting this stone that was originally at that cell to be one below it. It becomes here now because, again, there was nothing obstructing it. So in example 2, we have our input matrix or box, I guess, to be the following. It's going to be 4 by 2, and we output a 2 by 4 output matrix. Okay, and initially our cells would start, our 2 stones would start up here, and then 1 would be down here. Now this can't move anymore downward. Why? Because it's being obstructed by these 2 obstacles, right, which are denoted by these 2 asterisks. Now this, however, it can actually go down 1, right? This cell at this position, it was originally placed over here, but then we brought it down 1. Why? Because there was an empty cell below it that we can actually shift it to without being obstructed. However, this one could not have been moved downward because it was already obstructed by the cell below it, or rather by the rock or stone below it. So that's why we actually output a matrix of 2 by 4 instead of 4 by 2, with 1 stone up here, the other being empty, and other 2 stones right below it being obstructed by these final 2 blocking obstacles. And of course the last 2 cells at the very bottom are going to be empty because nothing even made it down there because of these 2 obstacles and these stones blocking each other. So in example 3, we have a lot larger of a box, just to kind of help us understand or grasp the concept of how this problem actually works, and we'd output just the opposite or reverse dimensions of our original matrix, with all the stones potentially being droppable 1 cell at a time down, until they're actually blocked by an obstacle or another stone right below it, or they just hit the very last row or index of our box, the bottom of our box. Now, with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to solve this problem efficiently, I know it may sound a little bit counterintuitive because we're given in the problem statement that gravity does not affect the obstacle's positions. But in this case, the best way to kind of think about this problem to solve it efficiently is to actually simulate the gravity for each row. And what am I really saying when I mean I'm simulating gravity for each row in our input box or matrix? I'm essentially suggesting that stones have to move rightward in our grid until they actually hit an obstacle or the boundary or the bottom or most bottom of our input box. Right? And once we've actually simulated this gravity, then we have to actually rotate our resulting box 90 degrees clockwise to actually return or produce the final grid that we want, right? The 90 degrees clockwise rotated grid. Okay, so I'm just going to break this down step by step. So let's go ahead and dive into the code here. So I'm going to first initialize my rows and columns like I do for most matrix and graph problems on Leetcode and in competitive programming in general. Rows and columns is going to be initialized to the length of our input matrix box and the length of our box at index 0. This is just a clever, kind of efficient way to actually store the number of columns and rows in our calls and rows variables respectively. Okay, so this is just going to help us iterate over our grid and be used for easy access as we actually kind of populate our grid. So now let's actually stimulate. I don't know if it's simulate or stimulate, I don't know. Well, now let's actually kind of stimulate our gravity, right? We're going to have an outer loop for rows, simply iterating through every single row of our grid. So we can do this quite simply for every row in the range of the number of rows we have, which we declared on the line above as the length of our input matrix box, as we stored in variables rows, simply again being the outer loop to iterate over all the different rows of the grid. We want to set our right pointer. I'm going to spell it like this, right pointer, to be initialized to columns -1, right? And what is this right pointer going to do? Well, it's going to keep track of the rightmost position where a stone, or in other words, a hashtag, can be placed in the current row. And initially, it's going to basically point or be initialized to our basically last column, right? Columns -1. And honestly, I kind of just wrote this as right pointer because we're essentially writing or overwriting every single cell with the next or adjacent up stone as we move it down. So that's why I call it right. And I know it sounds like right. I try to be kind of clever there. You can call it RIGHT if you really want. Honestly, it doesn't really matter. I just kind of did this because I wanted to actually kind of help you guys grasp the concept that we're writing or overwriting cells in our matrix with corresponding adjacent zones while they're actually non-obstructed and we can move them down in our input matrix. But it's okay. It doesn't really matter how you kind of set your name convention to be for this problem. So now that we've actually keep track of the rightmost position where a stone, again a hashtag, can actually be placed in our current row, now let's actually just iterate from the rightmost column, the inner loop for our column. So for every column, this is going to be nested loops by the way, in the range. And like I just said, I don't know if I said it just now, but we're going to iterate backwards, right? So columns -1, the last index of our columns, or the last column, we decrement by -1 each time. And we go up until -1 exclusive, or the 0th column, the initial upmost column, again decrementing by 1 each time, right? That's what these three parameters are actually telling us. Right? So to reiterate what this nested loop actually does, we're simply iterating from our rightmost column, which is initialized as columns -1 as our first parameter, to the leftmost column, which is going to be 0 or -1 exclusive in Python for for loops, right? And we're going to do this in our current row. We're iterating through these actual column values in our current row. So now we have to have or handle the first case when the current cell is a stone, which is again represented by a hash map. So in this iteration of these nested for loops, if the box at the current row column, right, again keep in mind row and column are our two iterators, in these nested loops at box row comma column if that's equal to a stone. And how do we know if it's equal to a stone? If it's actually equal to a string of a hashtag. And if that's the case, then we want to actually go through the procedure of first replacing this stone with an empty cell and moving our stone one down, right? While it's actually non-obstructable. So we'll set box at row, at column to be equal to a empty cell, which is represented by a period, or rather the string of a period, and we want to set box at row at the right pointer, okay, not R-I-G-H-T, it's W-R-I-T-E for me, to be equal to a hashtag, again, because we're simply moving our hashtag at the current cell one cell down if it's non-obstructable. And then we have to actually decrement our right pointer index by 1, indicating that we've just moved the current cell at the current index, or rather the current stone at the current cell. So to kind of reiterate a quick high-level rundown, what is this case, and what do these three lines actually do? Well, if our current cell, if it's actually a stone, or rather if it contains a stone, we first have to replace the stone, or the hashtag, with an empty space, rather an empty cell. Once we've done that, we want to move the stone at the current position pointed to, which is pointed to by the right pointer. We're simply moving it one down, okay, and marking that as a hashtag or as a stone. Once we've done that, we want to decrement our right pointer by 1. Why? Because we want to actually move it leftward, okay? Now, once we've done that, now we have to handle our second case. Well, what if our current cell, what if it's an asterisk, or in other words, a obstacle? So if, or rather, I'll have an else if conditional. So else if, or elif in Python, box at row comma column, the current cell that we're iterating over or scanning through, what if that's equal to an asterisk, right? This is the case of an obstacle, and I'm actually going to comment this out so it's a little bit easier for you guys to understand. This is going to be a stone case, and this is going to be the obstacle case. Okay, so what if the current cell, well, what if it's an obstacle? Okay, well, that's not good. Sorry about that. Okay, now, what if our current cell, well, what if it's an actual asterisk? Well, if the current cell is an obstacle, we first need to reset our right pointer to just before that obstacle, so the stone that we're moving doesn't actually obstruct with the obstacle. So, if that's the case, we want to set right pointer to be equal to column minus 1, which is basically the resetting of a right pointer, right? And that's because, again, stones can only fall up to this current obstacle and this current cell, and this is going to essentially make sure, as we're resetting this pointer, so that no stones actually move past it, right? Because of course that would be breaking the rules of this problem. That's exactly how an obstacle is defined to be. Right, and of course, if the cell is empty, we don't really need to have that case. If it's empty, we just simply continue without actually doing anything. Technically, I could have an else conditional and just say continue. This simply covers the cases when we don't have an obstacle or a stone, but we don't really need to do that. It's kind of redundant, right? It doesn't really going to change the code. It's unnecessary. So that's what we're going to do for actually handling cases when we have stones or obstacles in these cells as we iterate over our input box. Now we have to actually, well, rotate our box 90 degrees clockwise, right? That's the next step we have to do, right? Again, note that clockwise goes this direction. Feel free to just follow my cursor where I'm moving, right? Because the clock moves like this. And so clockwise 90 degrees is going to be like this. Okay, now we've done that. Again, now we have to actually rotate our box 90 degrees clockwise. So the way we're going to do this is I'm going to initialize my rotated box, which is essentially going to be the box output that I return. Okay, it's going to be initialized to an empty array, right? And again, this is going to store our final result after we actually rotate our updated grid to be 90 degrees clockwise. So now let's actually first have an outer loop for our columns, like we standardly do for rotating boxes 90 degrees clockwise, to iterate over each column in our original box. Not the rotated box that we're currently populating, but rather our original box that we're given as an input. So for every column, or per column, in the range of the number of columns there are, again, that we initialize up here, Again, see how it's very easy to access them without actually having to type length of column and length of box and length of box at index 0, right? Simply iterating over each column in our original box input. Now we first have to set our new row to be first initialized to an empty list, okay? Once we do that, now we have to actually start looping over the rows backwards for this current column. So for every row in the range starting from rows minus 1, I think it's row minus, okay. This is plural. It is rows minus 1, the very last row, right? Because that's going to be the last index of the row. Going up until the negative first exclusive row, or the 0th upmost row, and decrementing by 1 at each iteration, we want to add to our new row, or new row.append in Python, the box at the current column or cell. So at row, comma, column, or at row, index, column. So what do we actually do here? A quick kind of reiteration or high-level rundown. So for every column in our input board, or rather input box, we have to traverse the rows from bottom to top, right? Bottom up, right? And this is simply going to go over the rows bottom up from rows minus 1 up until row 0. Okay, decrementing by -1, or rather decrementing by 1, incrementing by -1 at each iteration. And once we do this, we simply have to append in this iteration each cell to our new row, right? It's effectively just creating a row in our rotated grid. Okay, so once we've done that, now we have to actually add our new row to our rotated box. Okay, so we can do that by simply adding to our rotated final result box, so result rotated box dot append the new row. Once we're done populating it outside of this for loop here. Okay, and effectively, once we've actually added the newly created row in this for loop to our final result rotated box, we can simply return our result, which is going to be stored in the rotated box, like we talked about before. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. Let's just check how it goes. And as you can see, this is just about as efficient as you can get. So, for a quick high-level rundown of how this code actually works, well, I know it may seem, again, a little counterintuitive, but we're simply basically simulating gravity, right? Because we know that stones actually fall to the rightmost available position that they're not being obstructed to in their corresponding row. And we have to stop at obstacles or our row boundary, or of course, if another stone is blocking it, right? And for our rotation, once we've actually done populating or adjusting or updating our original input, after we actually stimulate gravity, we have to rotate our grid by creating new rows based on columns of the updated grid, which we actually store every single new row with in our rotated box, which we ultimately return. And again, it's going to have the same dimensions as, of course, our input matrix, just reversed, or just opposite, right? It's going to have the same area, rather, okay? So, for the time complexity of this solution, this is going to be a big O of m times n solution. Why? Because, of course, the gravity simulation part of this program is going to be big O of rows times columns. Why? Again, because we're actually iterating over each cell exactly once. And for our actual rotation, it's also going to be big O of m times n, right? Because we have to iterate over every single cell. And so, the overall big O runtime complexity of this solution is going to be big O of m times n, or rows times columns, the number of rows we have in our input times the number of columns. And for our space complexity, we're going to have also a big O of rows times column memory complexity. Why? Because, well, we literally have to store an entirely new grid with the exact same area for the rotated result. And that's going to have dimensions of rows times columns, which is literally the same dimensions as our original input of rows times columns. And so our memory complexity is also going to be big O of rows times columns, again, because of this rotated box extra data structure, which is going to have, again, these same dimensions as our input. So, if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.